Okay, so just some context is, as you all know, I've been working on the NFSd direct stuff with Chuck and others, Jeff, and also there's the NFS client piece, but what we're talking about in this session is performance data that Jonathan Flynn has accumulated with various permutations of testing with NFSd direct versus buffered IO, and quite a bit of interesting data here, just in terms of raw performance and reduction in CPU and memory usage, but also Jonathan took it a step further and has incorporated PSI infrastructure to assess the pressure. The S in PSI stands for what?
Pressure stall information.
Yeah, there you go. Yep. And so he has a bunch of PSI graphs to look at that speak to memory and CPU and IO pressure building over time as the benchmark runs. So John, feel free to take it away.
Sure. All right. So just a quick look at test architecture. I like slides in some ways, but sometimes I like to just go straight into, like Excel and raw sheets. But sometimes it makes sense to have a quick picture that shows the architecture. Really, what I've got here is one client node and one server node running NFSv3. CPU memory spec is all there. Main node is memory on the backend server is 1 terabyte of memory. I have 8 Gen 5 ScaleFlux NVMe drives. They're spec'd at 14 gigabytes a second read and 11 gigabytes a second write. And so the idea here is that these NVMe drives are well suited to saturate the network. Network is composed of 2 ConnectX-7s connected at 400 gigabit each. Idea here is this is a kind of a hero performance lab, so we can show large scale and then scale down as needed. I am running Rocky 9.5 on both the client and the server with Mike's kernel enhancements on the NFS server side. So in the end, it's NFSv3, and I've simply exported each namespace of the NVMe drives as their own export. So in the end, I have 2 namespaces each, so 16 separate exports. So from the client side, that is 16 different mount commands. Since I have 2 networks, I, for simplicity, configured for 2 subnets. So I'm simply mounting 8 mounts over one subnet, 8 mounts over the other with NConnect 16. My network happens to be already make capable, so you'll notice that in there. But otherwise, fairly simple configuration. Let's see. Make sure I have a pen here. Okay. So just jumping into some initial results. What I will note here is I've configured for 2 data set sizes. One that's a little over 300% of memory. So remember, the memory on the previous slide at the server was 1 terabyte. And so in this case, the FIO, using FIO, I generated a 3 terabyte data set. And then we're comparing it to a 800 or so gigabyte data set, so 80% of memory. The only charts I'll have in the presentation here are simply the FIO results in regards to the application's apparent bandwidth and latency and stacks. On the left-hand side, you'll see bandwidth. And in this, some interesting items of note are from the 80% data set. We see that mode 0, buffered mode, and mode 2, the NFSd IO direct mode, show the same read performance when it comes to bandwidth. We can get into full details on FIO configuration if you like, but I don't want to waste too much of your time when I get into the numbers. We can also see on writes that there's no apparent difference in the write performance. So they both show similar read and write performance. When we scale up, from a bandwidth perspective, we scale memory up to over 300% of the backend, meaning we are pushing beyond the bounds of the capability of caching. We see that mode 0 drops down to 23.6 gigabytes a second, buffered mode, while the O-direct mode stays at the same performance as it previously was. Write performance tends to stay a little bit higher. I think this is tied to my NVMe drives being a little bit slower than my network, and so they keep the pressure off. But from the direct I/O mode, we maintain that same performance. So what's interesting here is that in the case where we're highly oversubscribed, meaning we are well outside of the bounds of the ability of memory to cache, we are able to maintain the performance with very little overhead. But the coolest thing here is that even when we are at the same at the capacity or below the ability to cache, there is no performance hit by going to mode 2 or direct I/O mode. And that's apparent in the latency results as well. We can see that latency shows exact same mean latency between mode 0 buffered and mode 2 direct I/O. Of course, though, once we get into that memory state where we are showing an oversubscription of memory, meaning a very large data set, the latency spikes very high for the buffered mode due to what we are seeing as contention, and I can show that in the spreadsheets here in a moment, where we maintain the similar performance to what we saw in the small data set previously. And the same goes for writes. Next slide, we'll talk a little about max latency, and then we can dig into a little bit of Grafana and a few spreadsheets. Any questions here as far as bandwidth and the mean latency goes?
Nope.
Okay. So some interesting notes as we move into max latency. As we saw in the previous slide, the mean and the max are very similar when we're talking about a data set that can fit within the buffer. But once we get to the point where we are oversubscribing the buffer or the system memory, we can see massive max latencies. This gives us a 1.35 millisecond latency combined with the lower performance that we saw on the previous slide. I have, from FIO perspective, I have all the latency bucket categorization as well as the nines latency categorization. That's just fascinating for deeper analysis. For writes, we also see that we're at close to 200 milliseconds for writes, whereas in the O-direct mode, we maintain the same latency that we saw previously, coming in at that at 32.7 milliseconds. So just really quick before we jump into more dynamic presentation, for those who aren't familiar with pressure stall information, thought it would be a good idea to cover it. The idea is it quantifies the amount of time where a thread is ready to perform a task, whether it's a memory access, I/O, or CPU, where it sits waiting for resources to become available. There are three categories that it presents. That's CPU, memory, as well as I/O. Those are all fairly apparent. The way it's reported, though, is in three categories or three metrics, and that's sum. That's at least one thread or one task has been stalled during a time segment. Full is a time segment in which all threads that are active have stalled due to one reason or another. And then total is a running count of microseconds in which in which threads were stalled during uptime of the system. In my case, I stepped back and I wrote my own collector with 1 second intervals, high resolution, and I calculated deltas for the total. So that allowed us to see how much time was wasted per second when we look at some of these spreadsheets where I've collated the data. Any questions on the pressure stall information before I jump over?
Nope.
All right. Just as FYI, I have a little bit more information. I don't know if we'll be able to get into it. One interesting perspective going forward is, how does all this work on a smaller shape system? This test right here, we can go into it if we have time, is one NFS share, one NVMe drive paired with the 400 gigabit network. And then the other one is, if we don't look at default memory management tunings, but we actually go through and do a massive effort to tune for memory management so that your K-swap D kicks in faster, your K-compact D kicks in faster and more aggressively. What does that mean from a performance perspective? And there were some positive results, but there's still some large gaps. Again, that's something that we can go into if we have desire or time. All right. So let's start here. So I have Grafana collecting node exporter data, as well as some an enhanced process exporter that I modified to be able to do regex matches of kernel strings. I'm not going to show any of the process exporter stuff. I'm going to keep it fairly fine-grained at the moment, and simply cover the node exporter stuff. What we see here is default memory mode with 16 volumes, as we described in the slide, with the 3 terabyte data set, so 300% the memory of the backend. On the left, we have our writes for mode 0, so buffered mode. Next over is our read workload for buffered mode, and then direct IO mode for write and direct IO mode for read. The main thing that we want to look at here is that our busy system is riding right around an 80% utilization during this time frame. And if we remember, the performance from the FIO was sitting around 26 to 30 gigabytes a second. If we compare, or sorry, this one was 42 gigabytes a second. When we compare to the direct IO, we see busy system is actually sitting at a 8.67%, and the rest has moved into IO wait. And this is providing that 72 gigabytes a second area of performance. When we look at read, our read was right around that 26 to 30 gigabytes a second. And this is on average, if we pick that middle point trying to, that comes in at that 71% busy system. And when we look at the mode 2 or direct IO mode, we see that that busy system comes in right around 12%. Performance being in the direct IO mode, that 93 to 98 gigabytes a second. Any questions here? Again, this is that macro view, but it's a really interesting view.
Nope.
All right. So 2 other panes that I like to point out here is, of course, memory, right? Here we show memory utilization in both the write and the read for mode 0, sitting at 100%. A little bit of dip at the end for the read workload. And of course, the mode 2 being direct IO is not going to use the page cache or buffer. We do see a slight rise over here in RAM used. And so that's an interesting case, but of course, the data path is slightly different, right? And then, of course, lastly, we have the NVMe perspective. What IO is actually hitting the disk? And so when it comes to the mode 0, the writes and the reads being negative, just showing both on the same chart, we can see that it's a very bursty workload. And I'll show you why here in a minute when we look at the spreadsheets that talk about stall information and the reclaims per second, scans per second, or steals and scans per second versus the compactions per second, that kind of thing. It's really fascinating. In direct IO mode, we're seeing a very consistent, very clean plateau. Just for your information, my scrape interval is 5 seconds. So with Prometheus, and so that's the resolution we're working at. So any spikes in between 5 seconds are hard to monitor, but this is a 5-second resolution. All right, so Where that leaves us is to actually look at the my data collector's results during these runs. What I'll do is I'll open up the mode 0 writes and the mode 2 writes, and we can do a quick comparison so we get familiar with these charts and can have a good idea of what we're looking at. Let's see. Okay, this is mode 2. All right. So this is the memory pressure stall information as given by PSI in the kernel. I've omitted the 60-second as it just it showed similar data, but it just cluttered the chart. So just quick education. Left-hand side is our bandwidth. That's going to be for total memory bandwidth, NVMe bandwidth, and NIC bandwidth. Those are orange, green, and dark blue. You'll notice that you can't see the NIC bandwidth. It's because it's directly under the NVMe and they overlap each other. The right-hand axis is percentage as reported by the PSI information. As far as the lines go, the light green and the blue, that's the 10-second interval average. And then, of course, this one that looks like black and pink are the 300-second information. When it comes to this, you'll notice that there's 2 lines in each. The upper line is typically the sum, and the bottom line is typically the full. Remember, full being that every thread who's trying to do something is blocked during any given time segment interval. So some interesting things of note on this slide are, first off, our NIC and memory bandwidth are indicating that 72 gigabytes a second during the first 18 seconds or so. My test procedure had me clear page cache at the beginning of every test. And so what we see is NVMe kicking in, filling, in this case, network kicking in and filling the memory as it writes to the NVMe. So we see a very nice high clean peak and plateau. And then once we get memory full, we see the pressure, stall information increasing substantially until it gets caught up. Once it gets a little bit caught up, we see pressure stall backing off. And you'll notice at the same time, our memory, the orange line, as well as our network and NVMe kicks in and gets faster again. As we get faster again, memory pressure on the memory begins to increase again. And so we see the memory pressure kick in and we see the performance trail off again. And we can see this repeated over and over again in the slide. What's interesting though is the amplitude is shrinking and we're starting to narrow in on a number at the end where we'll have a lower performance that remains somewhat stable. But any questions or thoughts on the pressure information from the memory perspective?
Well, it's pretty interesting, though. I mean, that's kind of what you'd expect. The proposed graphs, like out of phase, basically. So
Exactly.
You just see it on a graph. So
yeah.
Pretty cool.
Let's see, CPU information, it's interesting, but it's really tied to the, the pressure stall and threads trying to clean things up. The IO pressure is interesting because I want to compare it to the mode 2, the O direct mode. What we see during those first 18 to 20 seconds is IO pressure increasing exponentially. As soon as we hit memory pressure, we see the IO pressure drop off. So we can kind of see an inverse relationship between memory pressure and IO pressure. If memory pressure is high, IO pressure is low, and vice versa. Pressure totals is simply charting up those deltas in a percentage per second, right? So a good way to think of this is over here, for example, in the green line, which is my memory full percentage, meaning how much time did I waste waiting on memory, we can see that we're writing just under 40% on average. And so with that 40%, that would mean that I'm taking about 400 milliseconds out of every second and burning it, waiting for memory to become free so that my processes can continue. And again, you can see that inverse relationship of bandwidth, IO peaks when the memory pressure is low, like you saw with the pressure stall information. The next one is our memory management threads. Purple is K-compact-D, and it's the sum of all K-compact-D on my system. Because I'm an Intel system and I'm not faking NUMA nodes per socket, and I'm a dual socket system, I have 2 K-compact-D threads and I have 2 K-swap-D threads. What we see here is our K-compact-D in blue is writing just around 150, maybe 160%. And then at the end, it spikes up at around 500 seconds to right around to just below 200. Now, this is CPU percentage. And so with 2 threads, the max I can consume is 2 cores. And so 200% would indicate 2 cores. With K-compact-D, we can see it writing, just under 50, over here, just under about 35% for both. And at 500 seconds, it drops. Now, this is interesting, and I point this out, both the K-swap-D and the K-compact-D, because when we look at total reclaims per second and total compacts per second, we'll see some supporting evidence on why this may have happened. Now, here is reclaim information. The only line aside from bandwidth here is the total reclaims per second. Now, in this case, what that includes is K-swap-D and its scans and steals per second, as well as direct scans and steals per second. Direct being VFS or XFS or NFS, whichever threads will step in and help to scan and steal pages. And so in total, we can see peaks of scan and steal right around the 40 million mark. That one's 39 million operations, right, of scans and steals coming from both K-swap-D and direct. Direct is quite a bit lower. I can chart those up separately, but man, these charts get really cluttered when I add too many lines. And so again, what we can see is that same pattern of dips of scans and re-steals or steals when our bandwidth goes up, and then vice versa. So we end up with these interesting eyeball patterns as we go through. Now, you'll notice in that same time period at 500 seconds that our scans and re-steals drop quite a bit. But we saw in K-swap-D that our CPU utilization went up by about 15 to 20%. So if we jump over to the number of compactions per second, this is where it becomes really interesting, right? We have K-compact-D kick in at the beginning and keep a moderate workload. And remember, K-compact-D dropped off at the 500 second mark where K-swap-D kicked in. I don't exactly know how the memory mechanics work here, but this is the right workload. When we do reads, it's actually opposite. The K-compact-D is going to step in hard and K-swap-D will step down, but we see the same pattern of massive compactions. Compactions coming in here at 23,000 compactions per second. And that's the sum of completed compactions, stalled compactions, and requested, right? For compaction events per second. So really what we garner from this is that for writes, the memory pressure or the memory congestion has a direct impact on the performance, the IO performance of the storage subsystem, or in this case, NFSv3. So this is the right side. Any questions before I start drawing some comparisons with mode 2? All right.
Just a comment.
Yeah.
Maybe we should go back to 4K pages.
So this is
actually at Meta we had large folio support turned on in XFS, and they had to turn it off for certain cases because they found that fragmentation is worse.
Yeah.
So we're back to having these large pages that are hard to move around.
Well, that's what K-Combat D does, right?
Yeah. So it's supposed to,
Defragments the large pages, so.
yeah. So, yeah, it may be that we, large folios are not a universal win. Yeah, is what we're finding, I think. But inside, go ahead, Jonathan. I'm sorry. I didn't mean to
No, you're good. I mean, in fact, I think that's what's happening here is the fragmentation at the end and K-Compact just really kicking in hard, right?
Yeah, that makes sense.
Okay, so if we jump over to the write mode, now I had a 5-minute pause between workloads. And so what we see trailing off here are the 5-minute averages coming down from where they were. But generally speaking, what we see is our network, and you can kind of see it's not necessarily overlaid anymore. We can see the NVMe total gigabytes a second, and then right above it, the NIC IB total gigabytes a second, because remember, we're running Rocky. We can see those coming in at that 72, 73 gigabytes a second mark. Now, what's interesting here is because we're doing O-Direct and eliminating as many copies as we can, our memory performance is no longer 4 times larger than we saw with buffered mode. So I'm only doing 152 gigabytes a second in memory now. If we jump back over, because I neglected to point this out previously, down here we see that 72 gigabytes a second number, but our memory is way up here at the 292 gigabytes a second. So this is showing that we probably have 2 reads and 2 write operations happening in memory. And remember, my orange line is the sum. Again, I collect everything. Very low latency, like grep commands with a monotonic pause to ensure we target that interval rating. But anyhow, I can chart up reads and writes separately, but again, it shows that it's about 2 reads and about 2 writes in memory during that time period. Obviously, since we're not going through buffered, we don't see memory pressure kick in at all, right? Now, if you remember over here in buffered mode, our IO pressure would scaled up exponentially and then dropped off exponentially. When we look at IO pressure in mode 2 or direct IO, we can actually see a very consistent rise and both in the average 10-second and the average 300-second, with the 300-second converging simply because we're in IO wait. We're now dependent on the write performance of the NVMe drives. As far as pressure totals go, there's really nothing interesting here except you have the IO pressure total. Memory management threads, again, they're idle. IO reclaim and compact are also idle. And so as we look at all these compared to the other, we know that we have quiesced the system in a very high degree. And that explains, just jumping back to the CPU utilization, why we have so much time burnt in busy system in buffered mode versus the non-buffered mode or the O-Direct mode. So with that, I would jump over, and obviously you guys time check me, interrupt me, whatever you need to do. But the next one is, well, based on the FIO results, we showed that the 80% of memory, so 100% buffered or in memory, had no impact on performance. But what did it look like from a CPU memory perspective and resource utilization perspective at the host? So with that, I'll jump over here. So again, same pattern as before. We have mode 0 writes, mode 0 reads, mode 2 writes, mode 2 reads. On the writes, we can see an IO weight of about 50% and busy system at 37 to 38%. If we compare that to mode 2, we're sitting at busy system of 9%. So that's 1/4 of what it was. And our IO weight has gone all the way up to 70.8%. So we've effectively taken the pressure off of CPU and memory and put the pressure onto the storage subsystem, where, in this case, where it belongs, as these NVMe devices are so powerful. As far as the mode 0 read, we can see that IO weight peak as we're reading the data set into memory. And then we can see it goes straight to in-memory as there's no I/O wait. With this, we can see busy system writing at around 54%. When we compare that to the O-direct mode, we see that coming in as busy system 12%. So again, less than a quarter of the resource utilization, but providing the same performance in this case. And so this is really interesting. We also looked at the latency numbers, and so bandwidth and latency were approximately the same, but from a resource utilization perspective, we can see that the demand and load on the CPU and memory of the systems, well, CPU of the systems here, is substantially lower. If we jump over to memory, obviously we're bypassing, page cache in the O-direct mode. And so we go from about 80% utilized, that 832 gigabyte data set, down to nothing utilized with that same bump in the used, going from about 12 gigabytes to 30 gigabytes, or 5 to 30. And then lastly is obviously the storage throughput. Now this time, because we're not memory contentious, we see in the write performance a very nice clean plateau, because the memory is not contended. And then of course, since we are serving from buffer, we see absolutely no reads in the 100% buffered case. And of course, we have the same very nice plateaus that we saw previously in the larger data set sample. I think there were a couple pieces that were interesting from the spreadsheet side. Let me close the old ones and jump over to the 80%. Oh my goodness! Actually, before we do that, I didn't show you guys the profile from reads. I only showed you the writes. So jumping back to the 3x data set for reads. Our curves are a little bit different, which is fascinating. Okay, let's see here. It's mode 2, mode 0.
So, John, just so you're aware, we are, just over a half hour.
Sure.
Just so you know.
Yeah, that's perfect. Yeah.
Probably want to wrap it up soon, but this has been great.
Yeah, it's been cool.
Very cool. I'll breeze through this one. It requires a lot less explanation. We can see again the memory, the data set load into memory, and we can see us doing for the read workload. We can see doing about 97 gigabytes a second, both network and storage, and our memory is doing about 200 gigabytes a second. So that's interesting. The data path differences from read and write. We can see our memory pressure kick in very similarly to before. A bigger gap between full blockage and some blockage. But then we get out here to that 476 second range. And again, we see this massive spike in pressure, and pressure all the way up into that 80%, between 80 and 90% range. With that, we have pressure totals show a similar picture. We have got the memory management threads, but this time it's the inverse. Our K-swap D at that 476 second mark drops down in average utilization, whereas our K-compact D was very was very quiesced, but then jumped up during that time period. So what that should show us in reclaims is a fairly steady reclaim rate, but then of course the K-compact, the compacts per second kick in substantially.
So is that an indication that it wasn't just wasn't using large folios? Yeah.
It's a go. Sorry, go ahead, John.
Yeah, I mean, so the way the folios work, you can, if you don't use the full folio,
Yeah.
then it starts splitting it into multiple bits. And so I'm assuming that that's what triggers the K-compact D stuff.
Yeah.
At the end, you end up with sort of splitting your huge pages into lots and lots of
But when you see K-swap D going, that's K compact D not doing anything, that probably means you're scanning over small pages.
Yeah.
So that would be my interpretation. Yeah, so.
I think that there's definitely some additional investigation from the folio side to make sure that that's tuned well. As I mentioned earlier, I took a moment to ensure that I incremented from the mem-free bytes, kilobytes, that it's like default is only 256 meg, and increased it to about 0.4%, which I believe is understood to be best practice, which gives about a 4 gigabyte mem-free kilobyte kind of thing. As well as adjusted a series of other settings. I saw my latency profile stabilize. I saw this push out much further, but it was still converging. It was still converging to the same tune, but just a little bit higher performance with a little bit lower CPU overhead. But again, from the performance perspective on that one, which was interesting, my writes went up from 40 gigabytes a second to 50. So that was really good. I got about a 20% increase. My reads went from 23 to 26, right? So it was a very small read performance, but my max latency went from 1.3 second down to 360 milliseconds. And I'm going from memory there, but I can show you, I can show you what I'm talking about on that one, just in this slide. On the left, you've got default. On the right, you've got tuned. And then you have the two reads, 23, 26, 41, 52. Latencies are between latencies, average latency went down from 5.6 for the read to 5.50. So average latency went down a bit. Writes average latency also went down a bit, but this is the big one, right? That big outlier of 1.3 seconds went down to 380 milliseconds. And so that was one area where I looked at memory management tuning. What I haven't looked at fully yet is I am on a modified 612 kernel, but I don't know yet. I haven't looked at all the tuning procedures to ensure that I'm using folios as efficiently as possible.
I don't know that there are any good tunings for it yet.
Yeah, I agree. I mean, mainly what we did, at least at Meta, for these kind of workloads was just try to aggressively write back as fast as you can. And so we just tuned VM, what's the thing? VM,
Dirty ratio.
those things, tuned them just where they start right back as soon as possible.
Yeah, so here's where I played. I did mem-free bytes. This might be hard to read. Did mem-free bytes, water scale factor, swappiness, VFS cache pressure to try and keep more metadata and drop data. Dirty write back down to 1, dirty ratio to 3. Those, and then dirty write back centiseconds to 50, expire centiseconds 500, and reclaim zone to 0. And so those are the knobs that I played with, and that's how I got that extra write performance and the more stable read performance.
Yeah, makes sense. Yeah, unfortunately, I think the default VM tunings just haven't kept up with modern memory sizes very well.
Right. I mean, we're sort of doing we've gone from a model where we were only sort of using small pages, to a model where we're using larger ones, but we're still managing them as small pages.
Yes. And Joanne has been kind of struggling with this. You've seen some of her batches flying by on NFSv3. She was doing some work in this area about a lot of this stuff. And this is actually the same problem I think we're seeing with NFS, where like large folios sometimes just kill you because it's like the VM accounting doesn't account for the fact that they're large folios and like they should, we probably both Willie.
The whole need to migrate stuff is really an indication that we're doing something wrong.
Yeah.
Well, the interesting piece here, though, and I'd say it's been a fairly common paradigm that you put a cache layer in front of something because it's way too slow, and you may or may not want to convert to sequential IO, and there's a few other benefits, right? But when that backend storage layer or that backend layer that you're caching starts to hit the speed of the layer that you're caching with, you hit this paradigm of is it really appropriate anymore to cache? Because it is typically, rule of thumb is the goal, 20%. You're not going to do that with 122 terabyte NVMe drives, 60, 50, 30 or even 15 terabyte NVMe drives. 20% of some of these larger capacities. In my system, it's 50 terabyte. 20% of that is going to make memory cost, exponentially expensive, right? And so you can't hit a best practice ratio, and then you have NVMe that is more than capable of keeping up with your network. And so it's this design principle of, okay, well, if it's NVMe, perhaps the default is ODirect, because it will be obviously there's model generations and everything, but it should be a very stable, very solid, especially enterprise NVMe. But if it's hard drives or other storage devices, there is something to be said about defaulting to a buffered mode, right?
So, hi, Jonathan. I have one question. First of all, very interesting stuff. Thank you for sharing this. So you just a second ago showed your configuration of sysconfig. Now I'm surprised if you do direct IO, why you are patching dirty pages ratio and background ratios.
No, this is simply for the buffered comparison, right?
Oh, okay.
We wanted to be able to push buffered as far as it could go. And the main thing is to show, even with the tuning knobs that we have today, can we close the gap between buffered reads and writes and direct reads and writes? And the answer was yes, a little bit for writes. I was able to go from 42 to 51, and that's compared to the 72 that we achieved with direct IO. But with reads, we went from 23 to 26. It's a moderate improvement. But the main improvement for the reads was, of course, in the maximum latencies, the average latency, and getting a more stable profile. I honestly think, though, that if we increase from 10 minutes to an hour or 2 hours, this congestion profile that we see, this compaction and congestion, is going to only get worse and kick in more, right? If it's periodically, that's one thing, but we'll have bursts of performance and then sags in performance during large time periods. And so that's another potential area of exploration, is just let it run for 4 hours and see what the pattern looks like.
Thank you.
Just as you would expect, going to direct IO, clears everything up, right? Our memory pressure goes away. Our CPU utilization went down, as we saw in Grafana. These things ended up looking very clean and clear. Now, again, the answer here, the main thing that you would point out is, well, NFS is not just for high performance NFS servers. And so I wanted to take a minute and look at the OneDrive, and I don't need to get into that now. Just know I have the data that talks about a single NVMe drive that can only do 9 gigabytes a second and can only read at 14 gigabytes a second. And so what does that mean? And so I do have some comparison points there. I can dig into it a little bit now if you want. I do have some prepared, but I just know you guys are really busy out there, and I don't want to monopolize too much of your time.
Yeah. Maybe just give us the synopsis. Like, what does it look like on smaller machines? Yeah,
sure. Okay. So with that, I just jumped to this one slide. So this is apparent to the the application. Again, on the left, we've got bandwidth, mean latency in the middle, max latency on the right. This is the large data set again. I do have data on within memory. I just didn't have a chance to chart it. Finished my last run this morning. So, but I can talk to that in a moment. So as far as it goes, from a bandwidth perspective for reads, we see reads come, so that's the, at 3x, at 16, we've got 23.6 gigabytes a second. With OneDrive, we've got the 18.9. So in each category, we've got 16 volumes versus 1, so that you have a reference point to what we talked about before. So Now, what's interesting here is reads. I mentioned my drive can do 14 gigabytes a second. So in direct mode, I'm doing that 14.6. I'm getting the spec that the drive can do. But when I'm going through buffer, even though I'm a larger data set, I still seem to get a little bit of a boost from going through memory on the order of 5 gigabytes a second. Now, depending on how long I run my test, that may converge to the same level. Again, I only did 10-minute runs just to try and get enough data together to start seeing these patterns. From a write performance perspective, as I'm running synchronous I/O, just for my testing, the write performance was essentially the same between the two because we had to wait for acknowledgement from the NVMe device. There is something to be said about doing asynchronous and letting the memory flush as it can and just responding to the client, but this is with synchronous. As we move into
I guess the upshot here is though that this is not a universal win on small machines.
Right, exactly.
Okay,
well,
okay.
yeah. So yeah, with oversubscription.
That's good. That's good info. That's what we need to know because really what we're looking for, I think, as far as merging this is we need some way. We need some guidance for administrators to know when and how to enable these options, right?
Yeah. No,
because you don't want like people are going to go and see, oh, they've got this new feature. They're going to go turn it on. They're going to say, oh, this sucks. Or something because they have some shitty old machine, right?
Yeah, so I've got some ideas on writing up, a small write up on what's appropriate. What we see here is that as we look at the 1x, we can see latencies average latencies are about the same, a little bit better in mode 0, but max latencies show that mode 0 still can provide some outliers, right? And so the way I view this one is when you are larger than your page cache, it almost comes in as a wash, right? Especially for long-term runs. When you are smaller than page cache, as you would expect, because my read performance is only that of the NVMe drive, if I can fit entirely within page cache, I will get the speed of the network, right? Because the network is the next limiting factor. Typically not the memory speed, but the network speed. And so knowing my data, I know that this number for read jumped up to 47 for one 400 gigabit pipe. And so the one potential area of win that's a slam dunk for buffered is when you can do 100% cached reads. So your first read comes from NVMe, and it can stay in buffer for a long period of time. Otherwise, what I've found is, generally speaking, with all the tests that I've seen, the ODirect provides similar latencies, similar performance, while providing a much lower resource utilization. It's fascinating.
Very cool. Thank you. I'm gonna have to take off now, though. So.
Yeah, I think we're done now, Jonathan. Thanks a bunch, man.
Yeah, that's
No
great.
worries.
Thanks for all that info. That's really awesome.
Yeah, and I've got mountains of it and planning on putting into a share as well. Always appreciate any feedback we can get. So
think about writing a white paper, right? This would be actually a really cool thing to have a white paper for on your site or something.
That's exactly the thought. Is an academic white paper that kind of covers all of this, and then a blog post that simplifies it a little bit more. But yeah, sure, academic style with a blog post is definitely on the radar. Yeah,
because this is kind of stuff actually we want to be showing to the MM guys. I think because this is good info, and that might give them some ideas about how to improve things.
Completely agree, because even if you keep buffered for some and direct for others with good guidance, or even being able to deterministically choose, it will be any improvement in the memory management subsystem will improve things all around, right? So yeah.
Awesome, man. Well, thank you again.
No worries. It's good to meet you guys, and feel free to reach out with questions.
Take care, John.
All right. See ya.
Yes, sir.